It's important to realize that we have two cases we need to analyze, a uniform electric field, which would be this example, and a non-uniform field, the field as a result of a point charge. So instead of having two parallel plates and a nice uniform field between them, we have the charge concentrated at one point, and therefore the field is not uniform. If I were to draw the field lines in here, for a uniform field, for any field for that matter, we should remember that the positive charges are where the electric field starts, and they move or point in the direction of a negative charge. So for my uniform field, if I were to draw out my field lines, they should look something like this. I have my electric field leaving a positive charge, moving towards a negative charge, and this is because we test these fields with a positive test charge. If a positive test charge were placed at any location in this field, it will experience the same force in the same direction towards the negative plate. Now, a non-uniform field is a little bit different. We still have our field lines starting from a positive and moving away, but in this case, we'll have it moving in every direction as it's concentrated at one point, which is spherical, so this field will go off in every direction. Please remember that will be three-dimensional, so think of this as like a sea urchin almost. These lines are just used to represent the forces as best we can. We know that the spacing between these lines will give us the field strength, so we can see with this point charge, the spacing starts fairly close and gets wider as we move further out. So the further away we get from a charge, the farther apart the field lines are, which tells us that the electric field gets weaker the further we go out. In this uniform field, we have even spacing, therefore we know that we have a uniform electric field. The magnitude does not change. The force experienced by a charge in this field will not change. This will based on the distance from your charge, as is evidenced by the spacing between these field lines. Now, in terms of electric potential energy, it's important to realize that just like if you put a mass within a gravitational field, if you put a charge within a uniform field, a charge within an electric field, you will also experience some kind of potential energy. So for example, if I were to put a positive test charge right here, and I were to move it with the field, well, with the field is telling me I'm going in the same direction as the field. Well, you need to ask yourself, is this charge doing what it naturally wants to do? And this is something you have to always ask yourself. Is the charge doing what it naturally would like to do? This becomes one of the most important questions you're going to have to ask yourself anytime we're dealing with electric potential energy and whether a charge gained or lost said energy. You should already have this in your notes. You should be remembering this every time we come up with this. We've repeated it 1,000 times in class. But in case you missed it somehow, you always need to ask yourself, is this charge naturally doing what it wants to do? Okay, well, if the answer is yes, well, if it's doing what it naturally wants to do, that means it's losing energy. Just like if I were to take a mass and allow it to go with the gravitational field, if I were allowed it to drop towards the ground, it's going to lose gravitational potential energy. If I let my charge do what it naturally wants to do, it will lose. If it's doing the opposite, it must be gaining energy. Just like a mass naturally wants to fall, and if I raise it up, I increase its gravitational potential energy. If I were to take this positive charge and I were to move it with the field here, you can see that it's doing what it naturally wants to do. It would like to be near this negative plate, therefore it's losing. If I were to take a positive charge and I were to move it against the field, meaning the opposite direction, well, we should be able to see now that I'm forcing this in a situation it does not want to be in. Since it is not doing what it naturally wants to do, it must be gaining potential energy. Now, in terms of equating this, well, we have to again look at our two situations. We have both a uniform field and a non-uniform field. So in the case of a uniform field, we have a slightly different equation. We have our change in potential energy is going to be equal to the charge multiplied by the electric field strength that this charge is located in, multiplied by the distance that it is within this field, the distance that I have moved it is a better way to say it. So as an example, if I had, let's say I had a 4 microcoulomb charge, so 4 times 10 to the negative 6 coulombs. If I have a 4 microcoulomb charge, let's say I place it within an electric field of 2,000 newtons per coulomb, and I allow this to move, let's say 3 centimeters, which is equivalent to 0.03 meters. Well, what's happening over here is if I have a uniform electric field, well, we should know at this point my field lines will go in this direction. They leave a positive and move towards a negative. Well, this is telling me I'm taking my 4 microcoulomb charge, it's positive, and I'm moving it through a 2,000 Newton per coulomb electric field. And I'm moving it 0.03 meters. In this case, I'm going to assume I'm moving it up this way, 0.3 meters. So that's the distance that I've moved this up. I want to know what is the change in potential energy that's experienced by this charge. And the way I can do that is very simply using this equation. My change in potential energy will be equal to my charge, which is 4 microcoulombs. I will multiply it by my electric field strength, and I will multiply it by the distance that this charge moved. So if we take out our calculator and we take a look at this, let's see if I can slide this. There we go. So 4 times 10 to the negative 6, and I'm going to multiply that by 2,000, and I will multiply that by 0.03. And what I wind up with is 2.4 times 10 to the negative 4th. This is energy, so we're referring to it as joules. Now, did it gain or lose this energy? Well, in order to consider that, we'll have to take a look. I had a positive test charge. I moved it a certain distance against the field towards this positive plate. It does not want to be in that location, so this is the amount of energy that I gained. Okay, so it's important to realize there's a magnitude that we have, and whether we gained or lost that will be based on, is the charge doing what it naturally wants to do? We have to always come back to this question. We can look at a similar thing for a non-uniform field. If we have a non-uniform field, we could have, let's say, a point charge like this. We have our electric field coming off in every direction. This is a non-uniform field, and we have a slightly different equation from this that we derived in class. Well, in this case, we were told that our change in potential energy, or we derived in class that the change in potential energy is Coulomb's constant multiplied by the two charges in question divided by the distance between these charges. So as an example, if I, let's say, had a, if I had a 4 microcoulomb charge, so here is my 4 microcoulomb charge. Let's say that this was located, let's say, 5 centimeters from a, let's say, an 8 microcoulomb charge. So this big charge here is 8 microcoulombs. So I have an 8 microcoulomb charge. I have a 4 microcoulomb charge. They are 5 centimeters apart. So my question would be, what is the change in potential energy? As I essentially, if I move this 5 centimeters closer, how much energy is going to gain or lose? So if I move this charge 5 centimeters towards this charge, what will my change in potential energy be? Well, in order to look at that, we just have to simply use the equation we have. We know that my change in potential energy will be equal to Coulomb's constant, 8.99 times 10 to the 9th, times one of my charges. Won't matter what order, I will use my 4 microcoulomb charge first. 4 times 10 to the negative 6. I will multiply that by my second charge, which in this case is 8 microcoulombs. And I will divide all that by the distance between them, which we have to convert to meters, which will be 0.05 meters. That is 5 centimeters converted to meters. And if I take a look at that, I should determine, let's see, my potential energy should be, let's see here, K is 8.99 times 10 to the 9th. I'm going to multiply that by 4 times 10 to the negative 6, which is 4 microcoulombs. I will multiply that by 8 microcoulombs. And I will divide all of that by 0.05. And what I wind up with is 5.75. Since we're talking about energy here, that will be 5.75 joules. The question now becomes, did I gain or lose this energy? Well, in order to take that or consider that, we have to go all the way back to our original question. Is the charge doing what it naturally wants to do? If it is, it's losing. If it's not, then it's gaining. So if we go back here, we have 5.75 joules. We have a positive 4.86. We are moving it closer to a positive 8 microcoulomb charge. A positive does not want to be near a positive. Since I'm forcing it to do what it does not want to do, I must have gained this energy.